Welcome to iLecture Online, and our next topic in thermodynamics is the topic of entropy, and that's a very important topic in thermodynamics. So let's start with, first of all, that we use the letter S to define as entropy. And the definition for entropy, well, there's several of them. The first one, we can call it a measure of the amount of energy unavailable to do work. So in thermodynamics, we transfer energy from one to another, and usually during that process we can use available energy to do work. But once it's gone from a hot reservoir to a cold reservoir, it's no longer available. And so it's a measure of that unavailable energy. Secondly, we can also think of it in terms of a measure of disorder. Typically in the universe, things go from an orderly state to a disorderly state because of the exchange of energy. For example, if you put a block of ice somewhere in the middle of the street, after a while that block of ice will have melted because of the influx of energy. You add heat to the ice and it begins to melt. Ice is in a more ordered state because the atoms are locked in a lattice state. Water is a more disordered state because the molecules can roll over one another. So we go from order to disorder, and that would then be a measure of entropy, which means that the disorder has increased and the entropy is therefore increased. And throughout the universe, an exchange of energy usually results in an increase in the entropy. So what we usually try to do is measure or calculate that change in entropy. That little triangle there means change in. So we're looking for the change in the entropy, which is typically positive. And normally we calculate it by taking the integral of the exchanged heat divided by the temperature at which that occurs. Now, typically in more simple problems, the temperature is kept constant, and so we can find the change in the entropy by simply calculating the difference in the heat, or the amount of heat added to the object divided by the temperature of the object. Now be careful, dq, which means the change in the heat, is positive when the heat is added to the object, and dq is negative when it's removed from the object. All right, so let's do an example. Let's take the 1 kilogram of ice converting to water. Now, when we make ice melt, we have to add heat to it. And how much heat do we add? Well, that is the delta Q. Oops, my pen started drying up here. Delta Q is equal to the mass of the ice times the latent heat of fusion of the ice. So that is the amount that we need to put in there. And since we're adding heat to the ice, that quantity is positive. So this is going to be equal to the mass of the ice times the latent heat of fusion divided by the temperature at which this occurs. Now, of course, the ice is at 0 degrees centigrade. It doesn't change temperature when it turns into water, so the temperature there would be 0 degrees centigrade converted to Kelvin, which would be 273 Kelvin. All right, so this would be 1 kilogram times the latent heat of fusion. Now, that would be 4,186 joules per kilogram to change 1 kilogram of water 1 degree centigrade. We multiply that times 80, which gives us the latent heat of fusion for ice, for going from ice to water. And then we divide that, and of course that would be joules per kilogram. And then we have to divide that by the temperature, which is 273 Kelvin. Now notice that the kilogram cancels out, and we're left with joules per Kelvin, and those are indeed the units for change in entropy. All right, now let's calculate what that is. We have 4186 times 80, and we divide that by 273, and we're left with 1,227 joules per Kelvin. And that would be the change in the entropy of that ice when it turns into water. And once that happens, now it takes effort to take water and turn it back into ice. And so that would then, meaning that we now have a state where the entropy is greater, and it's greater by this quantity. And that's how you deal with entropy in thermodynamics.